Okay, welcome to Wednesday. Hope the homework assignment's going all right. I know a lot of you guys were in there last night. We're going to try to get some more TAs in there tonight to help out, and I'll be there for a little bit tonight to keep it going. Although I should expect this, but just waiting till the last minute to try to push through is not the best idea. But that's all right. We will have more people there tonight, and we'll do that. Yes, Rose. Yeah, good question. Yeah, the TA office hours go until. So there are a couple people at 9 and later.
Thank you.
To answer your question. Thanks, Bruce. Yeah, we'll put a couple more on. I mean, again, if you're having trouble and you don't have time to finish because of X, Y, and Z, email me. We'll figure something out. But I hope it's going well. I saw a lot of issues. Well, we'll talk about some of the issues a little bit today. But a lot of issues, again, with returning the wrong pointer and getting seg faults because of it. Once people fixed that up, it seemed to be helping out a little bit. OK, so today we're going to talk about first things first. So I screwed up on the make provide, the line that says make provide. You need an extra backslash on the second to last line of the provide part of the script. I guess I should actually show it to you. Let's see. Hopefully I have it here somewhere. Let's see. Drop Tufts, data structures, assignment 3, original solution, less makefile. OK, so there we go. OK, so this I think that slash is missing on your makefile. If you tried to do provide, it will provide all this stuff and then say you didn't provide enough files. Well, it's because these two files never get actually read in and submitted. So you need to have that extra slash there. I apologize. Backslash. Yes?
What about the two main CPPs?
Which two main CPPs? Oh, there's one there too? I don't think it matters, but you probably want to delete that too. It doesn't. I don't think it really matters though. Yeah. This is me doing the makefile too late at night. Yes?
Is provide working yet?
Provide is working. Yes. And if you do find any bugs, you put it on. Email me or put it on Piazza, and we'll figure it out. But it seems it should be good. Bruce did some good work doing that, putting that together. Anything else before I talk more about today? Makefile, provide, all that. OK. All right. So we're going to do a Unix tip of the day. I had a request to do a Unix tip of the day. There's a function or a little program called aspell, which is kind of cool. Some of the TAs will appreciate if you use this on your README file, because there are spelling mistakes in README files every so often. I'll show you one that does that. Then we'll talk briefly about debugging. Now, Bruce and I had this conversation yesterday. So obviously part of this class, a big part of this class is teaching you guys to read through code. This week's lab was instructive in saying, hey, look, you've got to read through somebody else's code, and you've got to go line by line. There are many times when you're programming that doing that, you either miss it because you wrote it, and it's like writing a term paper, and you try to proofread your own paper, and you're going to miss all sorts of stuff because you're the one who wrote it. There's issues with that. But what can help a lot of times is using a debugger. And we'll talk a little bit about that. Now, unfortunately, the lecture hall is not the best place to go through how to use a debugger. Although I showed you DDD before a little bit. To kind of go through and show you in lecture is not always the best use of our time, mainly because you're not really invested in it. Until you find a bug of your own that you can't figure out, that's the time when you go, oh, this debugger might come in handy, and you actually start to learn it. But I think if I can get my act together for next week's lab, we'll try to do a lab next week where you're learning how to use the debugger. And that will certainly help you on any future assignments if you want to. You don't want to use a debugger as a crutch so much as a tool to really help you out. I mean, you don't want to just throw it immediately into a debugger the first problem you have. You want to obviously be able to read code. But putting it in a debugger makes things like the following. I'm kind of overstepping what I'm going to talk about in a minute. If you're doing the event inputs for this homework, and you get to event 73, and something goes wrong with it, right? Well, you've got a whole bunch of stuff set up already by the time it gets to 73 that you get to it would be nice if you could go and say, what's happening right at event 73, and then step through the program. That's what a debugger will let you do. You can put a breakpoint on in the case where event 73 is coming in, and then you start running it right from there, and you can get the whole setup. So it makes it easier to debug when you have those kind of cases. So we'll talk a little bit about that. OK, and then we're going to start talking about these things called priority queues. It's another type of abstract data type that we're going to discuss a little bit about today. And then we're actually going to have kind of a break before we continue discussing them after spring break, actually, because next week we've got the midterm and the review session. So we'll keep talking about this now. But I'm going to do a little bit of setup for these things called priority queues today. OK, any questions so far? No? All right. So the Unix tip of the day. So I forget who asked me about it. Is the person here who asked me about it? It might be in the afternoon class. So here's this. There's this cool spell checker built into your to Unix basically. In fact, I don't know if you guys know, but in /user/ I'm going to get this wrong, share/dict maybe, yeah. There is a list of words right here. In fact, we're going to use this list later in class, right? And if you look at the word list, it actually starts out with a bunch of numbers on it, right? And then it starts going down, and it's got every word imaginable, right? This is like literally from Webster's Dictionary, some version or another, right? And it just goes on, and it's got, if you look, WC is word count, right? Word count words, it says there are 479,000 lines, which means there's 479,623 or maybe 22 different words in this dictionary. That's kind of cool. OK, so it's just built. It comes with the operating system, and you can use it. You can use it for things like the following. There's a spell, which I have to spell right, a spell. And if you do check and then say somebody's README file, which I hope I properly obfuscated or anonymized anyway, OK, what it does is it starts going through, and it actually picks out the word, what it thinks are incorrectly spelled words. Now, a bunch of them, like homework 2, and of course, if you put code in there, it's not going to pick up on a lot of that stuff. But it's really easy to ignore this. You just hit I, and it ignores it, right? It's going to hit all the CPPs and whatever, getters. Then it's going to hit some, and it's going to go, oh, ECT. I'm guessing the person who wrote this meant ETC, right? Now, I mean, does it really matter that much? Well, yeah, your README files want to be in proper English. So let's see, is ETC it is a suggest replacement, in fact, the first one. So if I hit the 1, it will actually replace it and go on to the next one. So it actually can go through this pretty quickly. Ignore, ignore, ignore. Oop, another ECT, right? Let's see, ignore, ignore, ignore. Another one. This person put a lot of ETCs in there, or ECTs in there. Makefile is OK. Ignore, oops. I forgot, I don't know, see what that one was. Ignore, ignore. Ah, look at that. Proceeds, right? And of course, the first guess is here. And remember what we were talking about with tries. There's a very good chance that like what's under the covers in this spelling app here is a try, because it just says, well, let's see, PROC. Do I have any words to start with that? Well, it looks at the try and goes PROC, and then it gives you all the different lists of PROC here ones. Well, there's only one in this case. And then it maybe backs up a little bit and tries to find words. There's also other various algorithms that it's going to use to get differences in letters and stuff, but you never know. So anyway, proceeds, 1, et cetera, et cetera, et cetera, right? And so this goes through, and then when you finally exit out, it will transferred is actually transferred, right? So this person didn't spell check, right? And so anyway, you do that, and then you can exit out, and it will actually save it will save the changes into your README file. Okay, kind of a cool little spell checker. Nice that's built in. Okay, not built into your Mac, I don't think, but you can download it for that. Any questions on that? Okay. All right, so let's go back here. All right, debuggers. So I kind of went over this a little bit. I've said this a billion times, right? Debugging is hard. It's probably the hardest part of programming. Like, you can come up with the algorithms all day and then put them into code, and then the question is, does your code work? Well, it's if it doesn't, it's probably because you made some little mistake with a pointer or some syntactical thing, or something where your logic might be perfectly fine. I've seen a lot of logic that isn't perfectly fine, but your logic might be perfectly fine, but doing the right steps and making it perfect is the tricky part. Okay, and homework 3 is a good example of that, I think, for a lot of people anyway. You need to be good at reading code. This debugger, and you can use GDB, you can use DDD, which is just a graphical version. It uses GDB to do all the stuff, the graphical version. Or if you have a Mac, you can use Xcode, which is a free download from Apple. And I showed a couple people this yesterday, and their eyes were like, whoa, that's really cool what you can do with that. You can just step through programs, and you can recompiles, and it's all built in. Xcode is actually an IDE, an integrated debugging environment, I believe that stands for, which tells you that it allows you to have all your files in one place in one window, and you can go back and forth to them very easily, and it'll recompile everything. So it's very neat, okay, to use that. Yeah, question. Yeah, that's a good question. Is it possible to connect Xcode to the server? Not directly. No, as far as I know. There may be some way, and there might be some plugin or something to do that, but I have not seen that before. There are other debuggers and IDEs that you can use that will do that remotely, but Xcode won't do it remotely, I don't believe. But honestly, all that you're really doing is once you get the program working, push it over to the server, make sure you test it on the server, and then it should work fine. Yeah. So the language is the same. We're writing what we call portable code in that sense, right? I can run it on my Mac or a Windows PC or a Linux PC, depending, as long as it has the basic libraries, you can do that. Yeah. OK, so that's what a debugger does. Again, what you can do with a debugger is you can set these things called breakpoints, which is really cool. You say, run your program, and then it will stop on a particular line, and like the one you say, and then you can step over to the next instruction and then the next instruction, and you can actually step into functions, meaning you can go into the function, it'll like go to the other file and then go into the function and then step through all the lines, and you can really trace your code. I mean, it's a real way of tracing your code, and you can print out all the different variables and things too, which is kind of cool. So you go, the event list. Is it supposed to the first event supposed to be January 1st, 2014? No, it's supposed to be April 25th or whatever it was, right? And you can see that right in there, right in the debugger. Okay? And you can watch them change as you go one line at a time. I mean, very powerful stuff. And definitely, once you learn how to use it, speeds up the debugging process, especially when you get to things like seg faults and all that. I mean, you can say, how far does my program get before it starts seg faulting? Back up a little bit and then walk it through. Okay? Again, I'm not going to show it to you right now. It doesn't really lend itself here, but hopefully next week or the next couple weeks in the lab, we'll try out debugging, see how it goes. Questions on that? No? All right. OK. So what else do I have here? Same. OK. So priority queues. So the next type of abstract data type, we're going to spend a fair amount of time on this because it's an interesting topic. Okay? Sometimes we want to store data in some sort of prioritized way. Okay? In other words, we want to store data based on some item that may or may not be directly from that object. So in the past, we've been storing integers, right? And we're always storing integers, and we're saying, well, like I forget, like on maybe day 2 or something, we talked about celebrity heights, right? All we stored in our data structure were the heights. Right? We didn't store celebrity names or whatever, but in some cases you might want to do that, like especially in the case of where you're trying to maybe make a list of heights versus the celebrity name. You want to store both of those things into your information. And we want to do it in a prioritized way. Real life, we have lots of times where we see priorities come up. Okay? Obviously, you see it in emergency waiting rooms, right? I mean, if you go in with a broken wrist, you're going to sit there for 4 hours. Because the guy who just like sliced his hand open, doing something is going to take precedence over you. It's going to have priority over you because, he might bleed out, and you're not going to, immediately die from a broken ankle, right? So emergency waiting rooms. Professor Hescott, who some of you guys know, mentioned this one to me. He said, "Look, your office hours are kind of a priority." Like you have the priority here. If I'm in my office hours and Bruce walks in and I'm talking to one of you guys, well, most of the time I'll stop talking to you for a minute and see what Bruce wants, right? Not because you're less important, but because Bruce is another professor, and that's kind of the way the priority works in that case, right? So I mean, the same thing would happen if somebody, if the president of the school walked in, right? I mean, we'd both stop and probably talk to him, right? So the priority does that. Another one that if you fly a lot, you might end up in this, getting on an airplane, right? So who gets priority on an airplane? Well, first they what's that? Military sometimes, military sometimes, if they're in uniform, and they generally do, and it depends on the airline too. But I've never found that to be that important for me anyway. And the other interesting thing, the military actually doesn't allow military members to fly first class in uniform, which is interesting, because they don't want it to look bad. Like, they don't want it to be like, look at this guy, he's like in the military and he's flying this first class seat and getting all the great benefits and what. So they kind of try to have you avoid doing that. But anyway, so obviously they say that families can go first, and if you're in first class or if you have some frequent flyer business, right, that's like the priority in getting on the plane. And then of course you go by rows, right, and they always try to do it from the back. There is a lot of research that actually has gone into how to properly seat a plane, right? And it's I read a couple years ago about an interesting one where it's the back of the plane one doesn't work quite as well as somehow you scatter them, and I don't know. It's maybe you try to figure. I know some airlines now actually say if you don't have any overhead carry-ons, you can go first, and that just like clears out a whole bunch of people right away, because they sit down, they're not fooling with it overhead. Anyway, it's all about priority, right? And figuring these things out is kind of important. And in real life, we have lots of different examples of this. Okay. All right. So a priority queue is much like a queue that we've already talked about, in that you have some object that's storing items, then you're going to maybe take them out in some particular order, right? But in the priority queue, we're not storing the elements in any particular order necessarily, except that we are storing them such that we store them by their priority, not by their other parts of their, however we define them. Okay? It's fundamentally different than a position-based structures that we've had. We're not storing them by position. Now, when you get down to it, yes, you're storing it by position, but the abstract data type part of it is not by the position. Like, you don't actually ever talk about the position in the interface to these priority queues. Okay? You solely talk about the position. And in fact, abstract data queues, the basic data queue, you're only allowed one position to know, or one item to know about at any one time. It's just like a stack, right? What item do you think is the one you want to know about? The highest priority. Or in this case, we're going to talk about the lowest number, which is the highest priority, right? So we're going to number them and say that the lowest number happens to be the highest priority. Okay, so that's how this one's going to be different. And that we don't have any real external notion of position. Internally to the data structure when we're building it, certainly we have to think about position if we're using an array or a linked list or something like that. Not so much a linked list, but we'll have to worry about that. But the outward-facing part of the algorithm, not worried about position. Okay. All right. So, anybody programmed in Python before? A couple people, right? Yeah. Python is really big in some of these ideas of having like another data structure we'll talk about later, which has these keys to elements, right? So a lot of applications require comparing and ranking objects according to a particular property, which we are going to call a key. Okay? The key is your property. Okay? You have a key, and sometimes you call it a value, sometimes you call it an element. But your key is what determines your where you're going to get ranked in this whole priority business. Okay? And this is not just priority queues. There's other things called dictionaries and maps and all these other types of data structures which we can talk about having a key for the data itself. Okay? It's going to become really important after spring break when we talk about some other data structures. Keys are not actually unique necessarily. Okay? You can have two different objects with the same key, which would mean the same priority, right? Based on the abstract data type, you can't pick out which one of those two is going to have higher priority. Otherwise, you would have changed their priority, right? So if you have two things that have the same key, well, as far as the abstract data types is concerned, it can give you either one back in any order. Okay, that's up to the internal structure of the data structure itself. Keys can change. So let's say you have some restaurant like ranking, right? Well, you could have you could base those orderings of the restaurant ranking based on some like Yelp rating, right? And the most number of 5s, or the cost, right? If you're gonna, if you want a cheap dinner, you're gonna sort things by the cost and not the necessarily the rating. There might be some kind of mix of the two. First, you might sort by one, then the other. Question?
So when we sort according to cost, for example, are we considering a different key of the same object, or are we changing the key of that?
Yeah, good question. When you sort by a particular key of an object, let's say, are you changing the key or using a different key? Depends on your data structure. You may have a restaurant which has 5 different keys. One's cost, one's Yelp rating, one's number of reviews, right? This is actually another big interesting point of research these days. Is maybe not a point of research. I've seen research on this before. You know how Amazon, like they rank you'd search for something and they always give you the top hits, right? Well, a lot of times, how do they base those top hits? It's on people, like the reviews, right? Well, have you ever gone to a product and it's like top reviewed product and this first one comes up and you look down at the reviews and there's like 3 reviews, right? And 2 of them are like 5s and 1 of them's a 4, and it's got this like really high like percentage of people that have rated it, but only a few people have actually rated it. That's not the best way to sort these things. I think Amazon still actually does it that way. What they want to do is find the one that has the most reviews and then sort kind of by most reviews first and then by the best of the most reviews. And they have some sort of algorithm for doing that. But that's definitely, you have to think about different types of keys when you're talking about that. Okay? All right, so that's what a key is. When you have an element and you have some key that's based on it. Okay? All right, so we said keys can have more than one value. There could be a passenger on a plane, right? And this is exactly what you were saying. I mean, if you want to compare, you can compare that passenger against some other passenger by what fare that person paid. Generally, they give the person who paid the highest fare the first priority in terms of like getting bumped onto or getting pushed onto a standby flight or whatever. Right? Check-in time. You came really early and checked in early, they put you at the front of the list based on some priority. Frequent flyer status, etc. So you can have lots of different keys. Okay? You can generate those keys by either some property of the object. So let's say you're looking at cost of a book. Right? If you have a cost of a book, well, that book has some particular cost, and that's what the key might be based on. Right? Or the weight of a car, if you're somehow saying, I want cars that are less weight because I get better gas mileage or something like that. Right? You can do that. Or you can actually generate them by the application. So like the gate agent, right? You come walking up and the gate agent kind of looks at you and goes, and starts furiously typing, right? Well, she's looking up what your like frequent flyer status is, how much you paid for the fare, where, in order to prioritize yourself or prioritize you, right? So that's not necessarily based on like a property of yours. It's based on some other algorithm that gets used. Okay? Questions on that? Not so bad. Okay, so this is all set up right now about why we need to worry about these priority queue things. Okay? At some point, you're going to have to compare your keys. Okay? Comparing keys when they're integers is really easy, right? Comparing keys when they're like ratings is not necessarily quite as easy. I mean, you can take an absolute value of you can take the actual value of the rating and do that, but like we talked about with Amazon, there's other things that might go into it, right? If you are going to do comparisons for keys, you need to have some non-contradicting comparison rules. In other words, you have to be able to write some rule that says the following 3 things. And they're called properties. This is kind of mathy, I suppose, but first property is the reflexive property, which is a pretty simple one. Some key is always less than or equal to itself, right? You have to be able to define that. You have to be able to compare. So if you compared 2 keys, there can't be a situation where your algorithm sometimes makes one less than the other if they're the same. You can't do that. You have to say either they're less than or equal. There's another property that's called the anti-symmetric property. Here's what it says. If K1 is less than or equal to K2, and K2 is less than or equal to K1, then it turns out that k1 has to be equal to k2. Think through that one for a second, right? If it's less than or equal, and the other one's less than or equal, has to be equal, right? If you just compared less thans, well, then you'll miss some of the equals part of it. But if it's less than or equal, then you end up with saying that they're the equal key. And then finally, there's this other property called the transitive property, which is this. And this is the one that might, again, seem kind of obvious. k1 is less than or equal to k2, and k2 is less than or equal to some other k3. Therefore, k1 has to be less than or equal to k3. No, that one I hope makes sense. Yes?
So I don't understand. Is this what we should do when we're comparing, or is this like what we should?
Well, yeah, good question. So this is digging a little deeper than some of the stuff we'll do initially. But when you are comparing items, you have to be able to make these comparisons every single time be the same, such that these three rules work. So you can't ever have a case where you're comparing things, and if you do k1 less than or equal to k2 and k2 less than or equal to k3, somehow k1 is actually greater than k3. You've got to figure out your comparison methods such that it does that. Now, again, for integers or for, well, I mean, anything that's based on an integer, it's easy to do, and that's just regular old mathematical rules. But if you want to have a comparison for other types of keys, you have to think about these things. You have to always kind of think, OK, do these three properties hold for any kind of comparison I'm going to make? I'll have to come up with a specific example where it's not easy to do this, but you have to think about these things. OK? Any other questions on that one? OK. All right. Yeah? Yes? Well, yeah, I mean, k could change, but if you have two instances that are both k, they have to be less than or equal to each other. I mean, they have to be equal to each other, right? You can't, once you change one, the other one has to change, or it's not the same key anymore. That's really the only thing, yeah. Good. I might have missed that. Hang on. Nope, I didn't. Why is it, let's see. K is less than or equal to k. Well, that means that k equals k. Yeah, I probably should have put that in there. Yeah. Yep. But in other words, if you're comparing, yeah, you're right. I mean, it should be equal to, I suppose. Yeah. In that case. I mean, I guess there's probably cases where if you're doing this less than or equal to comparison, in the end, if you're going to just report that it's less than, that's fine if they're the same key. Just like kind of what we did with the events. Remember how we had events that you would always say, am I before? No, you're not before if you're the same time, right? So kind of maybe that mentality. Good, yeah, good question, though. Anything else in this one? OK. All right. So our comparison rule, because we have those three situations, this means that we actually can order everything linearly. If you have a whole bunch of whatevers, events, whatevers, right? You're going to have a relationship where you can order them. Now, again, things that are the same could be in some, when the keys are the same, you're not going to be able to tell the difference between them unless you use some other key. But otherwise, we can have an ordering relationship where we can definitely have a smallest key, could be shared by many elements, right, such that the minimum is less than or equal to every other key. Again, this is not rocket science, right? This is basically saying you have this whole group of keys. One of them is going to be the minimum, or more than one of them is going to be the minimum. Could be all of them. They all happen to be the same key. Yes, Remy?
I think in the previous slide, you wanted to say it is smaller than or equal to, because your comparison rule is smaller than or equal to.
Which one?
In the previous.
For that one, yeah, I think you're right.
Yeah.
You do want to be OK. So it should be less than or equal to. It is, yeah. OK. All right. But anyway, so all this is saying is you can find a minimum one. Again, not rocket science in this case. OK. So the actual abstract data type, a priority queue, is a container of elements, which we have seen many times already in this class. OK. Each having some key that is provided at the time the element is inserted. Now, you can change it, but if you change it, you'd better you have to take it out and reinsert it with a new key is basically what you need to do. Okay? You can change the key, but you have to figure out why. You have to end up with a situation where you can't change it while it's in the structure. You can change it at some time if you take it out and put it back in. Okay? The keys obviously determine the priority of these elements that are, or the priority used to pick the elements to be removed. Okay? Again, this is all set up so far. Okay? You can, and again, these are all online, all these slides. I see people furiously writing, but I'll try to make sure you have enough time to write. Keys determine the priority. OK, well, that's not bad. And by the way, have we seen any of this sort of thing before for programs we've already written? Which one?
Ordered sorting.
Ordered sorting. We haven't really done sorting except that we've put things into a list in an ordered way, haven't we? Yeah. When you print out your event list, right, well, it's hopefully in ascending order, which is what you want. And that's kind of the same thing. So we've kind of already seen this, but not really directly talked about it, right? We've had more or less keys based on just the integer value of, say, the start time, and the elements are like the end time and the description. So yeah, we've kind of already seen this in a little bit. Yeah.
So in a priority queue, every element has its own key, and all those keys measure the same metric.
Yes, that's a very good way of putting it. In a priority queue, every element has its own key, and those keys measure the same metric. That's a very good way of putting it. Yep, absolutely. OK. All right, so we're getting there. Priority queues, much like our other data structures, have fundamental operations. The nice thing about priority queues is, much like a stack and a queue, those operations are limited, which means that we can generally make them, like we can use the property of the fact that they're limited to doing only a certain thing so that we can hopefully speed things up instead of, based on some other like unordered lists or something like that. Right? Or other just containers or sequences that don't necessarily have orders. These are the three fundamental operations. Insert item. OK, you give it a key and you give it an element. OK? And you insert the element E with that key into some P, which we're calling the priority queue. OK? Insert item. We're going to write these functions in a little bit. OK? Min element. That sounds kind of like a binary tree sort of function, right? You want to find the minimum element. Why do you want to find the minimum element? That's the only one you're allowed to find, right? You get to query the data structure and say, which element is your minimum element? That's nice. OK? And then you can also remove the minimum. In a priority queue, a straight-up priority queue, you cannot remove the maximum. Now, you could build some sort of queue which does that, but it wouldn't be a priority queue anymore. Yes? Good question. What if there's more than one element that has the same minimum? Different data structure implementations do it differently. I've seen it where it just deletes the first one that it happens to find, and you don't know which one that's going to be, right? I've seen other ones where it deletes all of them that are that minimum, right? And in the big picture, that's not that hard to differentiate, because if you can find the minimum, you can certainly find the next one after you remove it and whatever. Kind of like our stack ADT that we saw, the template functions we saw back in lab a couple weeks ago, minimum element does not remove it from the tree. It's kind of from the priority queue. It kind of gets to peek at it, but it doesn't remove it. Okay, remove min actually does the removing. You could certainly come up with another function that could remove it, to look at it, like remove it and return it to you if you wanted. It's not part of the overall operation. Okay? All right. So we've got three main fundamental operations. Of course, there are other operations that we get with a lot of these data structures. These ones are not so fundamental in that, you need them for the operations, but they're not the ones that we're really too concerned about. Size, that's easy. As you're inserting into some priority queue, you keep the size. We've done that before. Is empty is a good one. You need to know how many there are. Again, you're keeping the size. So if size is 0, it's empty. OK. Min key. So last time we had min element. Now we've got min key. It might be interesting to know what the minimum key is, right? So you're doing some statistical analysis on the Amazon ratings, and they're all by rating, and you want to go, what's the best rating you can actually get, right? Do any of such and such have a perfect 5.0 rating where every review is 5, right? So you'd be able to get you'd actually get to say, what is the actual minimum key in there? Might be important for some reason or another. You could probably think of other reasons. Anybody think of another reason why it might be nice to know what the minimum key is versus the minimum element? Think about that for a minute. Yeah.
Like maybe for debugging purposes, if you know what the min key should be.
So for debugging purposes, knowing the min key, yeah. I'm thinking less about the like writing the program, but more about the bigger picture, like somebody using one of these. Why would you necessarily care about what the minimum key is if you're putting in there? Yeah.
Or if you know that you want to insert an element that has a higher priority.
Yeah, that's good. If you want to know you want to insert an element that has a high priority. Did you guys watch the Winter Olympics a couple weeks ago, right? And I didn't like watch too much of it this time, but at least in the past, it's always been true that for things like the figure skating, where they have to like give people actual scores, people at the first scores that they start giving are going to be relatively low. And then if that person happens to be the best, all the other scores will hopefully fall lower than that person's score, right? So if the first person goes out the gate and is amazing, you don't want to give them like a perfect score at the top, because then you have nowhere to go up, right? You have nowhere to make that score better. So in this case, it might be nice to say, this skater was awesome and way better than all the other skaters. What's the best score, or in this case, the minimum key, that, if we're making it 0-based or something, what's the minimum, so that we can find something lower than that? Yeah, that's a very good idea. Yeah, good idea. So you might want to know that. Okay? All right. And this is kind of important. The book I happen to look in to get some of this stuff, it talks about the fact that it returns a constant reference. That actually means that, look, you can look at the key, you can't change it, right? You can't, and this is what we talked about before. You can't change the key midstream. Like, you can't say it's in the tree, I'm gonna adjust it now. You have to kind of take it out and then put it back in with the proper key. Okay? You can't do that. All right. Okay. So it turns out, and because there's only really 3 important functions that we're really going to like, that are the meat of these kind of functions, and we don't need to worry about position, these 3 types of functions are the only ones we need. We don't need an insert at the beginning, or an insert at the end, or a delete from beginning, or whatever, which we did when we did sequences. I don't know if you recall, there's all these special cases and things with sequences where you have to do these, you have to worry about the fact that it's the first one or the last one. You do in some of the roots of when you're actually programming this too, to some extent. But as far as the data structure itself is concerned, you need to worry about these 3. The other ones are pretty easy to tag on, and that's it. So it's pretty simple. This simplification will help us out later when we're actually looking at how to make this better, how to make these priority keys better. And there's only one insert and delete function, okay? Which we also had in some other data structures. I mean, trees only had one insert and delete, right? But this is a slightly separate type of function. Okay? All right. Let's go through a quick example here of inserting into or dealing with elements in a priority queue. Okay? All right. So we're going to have an operation. We're going to have the output of the queue, and we're going to have the actual what it's actually looking like. Now, technically, you're not allowed to in most implementations of priority queues, they don't actually allow you to like say print out the queue, right? In the sense that you can't get like the actual underneath the covers ordering of this thing, right? If you want to print it out, it will print it out by removing one element at a time, and then you can do what you want with that, because you're only allowed to remove them in. You're not allowed to like look at position 82 because you have no idea how it's built, right? And that's another key to a lot of this stuff, is you don't know how these things are done under the covers, but that's by design. Okay, so that the person who's designing it gets to make those decisions and make it more efficient. Okay. All right, so let's see. So if we insert item 5 and A, this is the key, this is the actual element. Okay, in this case, all right, we don't get any output. This is what's in the queue. Check. Do the same thing for a couple other ones here. 9 goes in here, 3 goes in here, 7 goes in here. Does it matter what order they are over here? Not for the abstract data type as a whole, right? How you store it on the back is irrelevant. at least for the actual, what, like correctness. For correctness, how you store it back here is not relevant. Okay? So we insert all those, and we get 5a, 9c, 3b, 7d. So far, so good. Okay? All right. Then we find the min element. Well, what it does, it goes and says, this is the min key, so that's got to be the min element. Depending on how you implement this, it's the same idea. You have to somehow get through this list, right? Depending on how you develop this priority queue, you have to somehow get through this list and figure out which one has the minimum key, and then return the value that's the minimum element if you're going to do this. Okay, min element, B, gets returned. Does not remove it from the priority queue. Okay, all right, I think I go to the next page here. Nope, not quite. Min key is 3, same deal. Can you ask what the max key is? No, you can't. You can't ask what the max key is. You can't ask which, what element 4 is or whatever. You can't say what's the last one. You just get those types of operations. Okay, so we're still going along here. Remove min. Well, you can. Remove min. Min was in this case the 3, right? So it removed it, and now that one's gone. Removes it by key, not by the fact that it happened to be B, right? That irrelevant, just by key. Okay. All right, size. Well, easy enough, 3. Min element, same thing. It's going to now pick out the min element, find the min element here, and it's going to be A. Okay. Remove min, same thing. Remove min, same thing. Remove min, same thing, and now we've removed everybody. We don't actually get those values. If we wanted to figure out what 9 and 7 were, we would have to say first min element, then remove min element, remove min, min element, remove min. Okay. All right, questions on that? Pretty straightforward. The next one, what if I tried to remove min again? Error, right? You can't remove it. In your program, you could either print out error, or you could print out something like or do an assertion, for instance, and crash the program if you're allowed to do that in your data structure. The person using this data structure needs to keep track of whether or not it's empty in that sense. Okay, fair enough. All right, and then I guess we could do one more. This would crash if we had the assert, but you could also say is empty. In this case, it's true. Okay. Questions on what the abstract data type for a priority queue looks like in the big picture? We're going to go and dig into some code and actually build this and see some results now. Yes? Yeah. Do you need to sort the queue? You do not need to sort the queue. It's in the big picture, you don't need to sort the queue as far as the interface is concerned. Remember, the interface gets to say remove min element, it gets to say these things, does not get to say sort the queue. Can you think of a way, can you think of how we might get a sorted result from a priority queue? Let's say we wanted to sort everything in the queue. What kind of algorithm could we walk through to actually get a sorted result? Yeah. Yeah. You create a new list. That's perfect. You create a new list. Call remove min in a loop through all the elements. Put those removals that you get back into a new list, and guess what? You just did your first sorting algorithm. Right? It actually works. Works great in this case. So yeah, I mean, it works great. We haven't talked about asymptotic behavior yet, but that is a very good way to do it in this case. Okay, so yeah, it's kind of interesting. So yeah, so to answer your question, could be, you don't have to actually sort it in the priority queue, but maybe the priority queue is a good place to figure out how to sort it. Yeah.
I mean, because we had to compare, in order to do the remove min, we had to compare all the elements anyway.
Yeah, if it's not, that's a very good point. If it's not sorted, and you have to do you want to do remove min, how many elements do you have to compare with? Yeah.
If you're inserting it and you keep track of the min key while you're inserting, like a pointer to the address of the min key.
Oh, well, you keep an address to the min key.
At all times. Like whenever you're inserting, you compare the
Oh, I see. Oh, okay. That's not a bad idea. Not a bad idea. Keep a pointer to that, but then you remove that one. What happens to the next one? You move, well, okay. You move the pointer, but you have to search through all the elements, right? So yeah. So yeah. You'll get the benefit of that once, right? And actually, it's an interesting point. I mean, so if you were using, this is actually kind of a little sidetrack. If you were doing something like that, and so to reiterate, let's say that you're clever and you say, I know that the next thing the person's going to ask for is the minimum. If I keep a pointer to that minimum, or min, right, then maybe the next time I will I'll return immediately to the person, right? So let's say you're doing some parallel system where you could return a value and then keep working on some stuff. If you wanted to and you were doing a removal, you would get the value back immediately and then in the background like do all that extra like finding out. So yeah, so doing that's not a bad idea, really. I mean, in some cases it's not a bad idea. You do eventually have to walk through to find the next minimum though, right? And that's actually the case, isn't it? Right? You have to walk through all the elements to get to the minimum one. If you don't know where it is by some sort of position that you've kept, don't you have to check every single element in this form anyway? In this form you do. Yeah.
Can you keep it as a linked list?
Can you keep it as a linked list? Sure.
Your head is the smallest.
OK, but then you're keeping an ordered linked list, right? So that's fine, but you have to. But you can do it. But again, you have to keep an ordered linked list, and maybe that's a good idea. OK, we're going to build this in a second. We'll look at the trade-offs between keeping it ordered or not, and we'll see some trade-offs here. OK, we'll see what that happens. All right. Any other questions on the big picture here before we look at a little bit of code? OK. All right. So let's implement this. This should look somewhat familiar, right? I mean, this is, we're going to call it priority queue unordered list. That's kind of a long name. But in there, we would have a struct that is the maybe. You could either have a struct or you could just have a couple elements that are in the actual private data, right? That would be priority object, we'll call it. It's got a key and it's got an element. No pointers here for this one. If you wanted to do this with nodes, you could certainly do it with a linked list. It would look a little different, but same idea. Okay? So this is part of our header file. In our header file, of course, we're going to have all of our various public methods here, or public methods here and things. We're going to have some. If I'm doing this, I'm going to use a dynamic array for this. Okay? You could use a linked list. Okay? We're going to have the constructor. We're going to have some of all the different functions that we need. I threw this one in. When you look at if you want to look at the code online, it's a little ugly right now. The main function is kind of ugly because of some of the tests I wanted to do. But you can look at it. But I put this in here just so you'd be able to actually see the printout of it. You should not get this in a real version of a priority queue. You should not get the ability to do this. It's not good data hiding in that sense. Okay, but we've got the other ones in here. Okay, most of them are pretty easy. I mean, size is really easy. It's just return the size because you're keeping that around, as you go. The private stuff here, in this case, I decide, OK, I'm going to make it a dynamic array. So I'm going to keep the thing. This should look very familiar at this point. We're going to keep the size, capacity. We're going to have an expand function. Why not? I'm also going to keep have a private method, which I'm going to call min_index. Because I'm using a data structure, I'm using a dynamic array, indexes are kind of important for knowing where in that array things are. And it's going to save us a little time later when we want to, instead of just using that min element, to actually under the covers have this min index. But it's just under the covers. That's why I'm making it private. Okay? All right. Let's look at our three different operations. Insert item. Okay, let's look at this one. Insert item says insert k. In this case, it's an integer. Could be any kind of size type or whatever you want that tells you how big something is, or that you can compare with. Our string, which is going to be the element. In this case, it's going to be a string. First things first, expand if you need to. Should be very familiar at this point. And then I'm just going to say, look, insert at the end. If I don't need to keep this sorted, and I can insert at the end, do I need to do any movement of data? for an unordered list when I'm inserting? I do not. Right? I just insert at the end. I say, look, the key is going to be at the end here in our element at the end, our key, our element at the end. Our element actually goes in the same position in our remember, this is a priority queue of that structure, which was priority queue, whatever it was. I forget the name of it. It was this. It was a priority object. So in our priority object, we are going to store a key and an element at the end, increment this. Not bad. Okay? In fact, we kind of like this. Why do we like this? What is the asymptotic behavior of this? What big O notation would this be? Oh, what? Yeah. So I'll write this down. This is going to be insert item, right? And it's KE, right, is O1 for the unordered list. Unordered list. OK. Why is it O1? Because you don't need to go through any of the elements. There could be a million elements in there. All you need to do is go to the last one, plop it right there, you're done. Great. We love that. We can get a constant time asymptotic behavior. We are very, very happy. OK? Because that's great. OK. So that's the insert. Let's look at min element. Now, this is where I did this sneaky thing, and I used the min index here. OK? I said, I'm going to use in my min element function, I'm going to return the item at the min index, which I'm going to call up here. OK, I did this for a reason. If I wanted to find the min key, and I walked through the whole list and found it and then returned just the key, and then I want to return the min element, what do I have to do again? Walk through the whole thing again, right? If I do instead have just the index, well, then I can return the index. And this is a really pretty easy function, right? I return the index, and then later I can say, oh, now behind the covers, I'm going to return the actual values based on that index. OK? And you'll see why this is actually kind of interesting later when we get to the next part of this code. OK, and remember, this is the unordered priority queue implementation. OK? All right, so how do we find the min index? It's pretty easy. You walk through all the elements. And do you have to walk through all the elements? Again, you have to walk through every element. Why? Because the last one could be the minimum. And you just don't know until you get there. And you could store it, but then you'd have to walk through to find the next one or whatever. But you'd have to walk through every one. OK. And the min index, and then you return the min index. And this one just returns this. OK. So the actual min element part is very straightforward. This, what is the asymptotic behavior of this guy? Oh, what? Oh, n, right? So this one is min element. Min element, right, is O n in this case. All right? So it's O n, and we know that because we have to walk through the whole list. Right? And I'm putting boo because n is not a terrible thing, but if you're doing lots of operations, it can get ugly fast. Right? It can get ugly fast. Yes? Remember we did this the other day we had a very similar function the other day. The first element could be the element we're looking for, right? So the first thing I'm doing is setting the index to the first element, and then I don't need to check it against anything else. It's either the first one or it's either the first or the second one, let's say. And the first one, if I set it the first, then I can walk from one up. It just saves me a step. OK? All right. Order n, boo. OK, we don't love that. All right, let's see the delete or remove min. Removing from a dynamic array. OK, you want to remove the one here. What do you have to do to everybody else? Shift back by 1. I saw lots of people doing that wrong on some homework things. You eventually fixed it, but shift it back by 1, right? And that's the part where you do it. What is the asymptotic behavior of that? If it was the first element, let's say the first one was the one that you had that happened to be the one you want to remove. Yeah? What's that? If it's the first one you want to remove, you find it quickly, but then what do you have to do? Move everybody else back one. If it was the last element, what do you have to do? find it, and then move none of them, right? So what's the overall asymptotic behavior here? On again, right? OK, so remove min, right, is also on. OK. All right, which we get a boo for that as well. OK, because we don't really like that, and that takes up some time, and it's not great for your behavior if you have lots of items. OK. We had the question earlier. What if we just kept this thing ordered? Wouldn't that make our life that much better? Maybe it would. OK, let's do that. Let's check and implement this in an ordered list instead. Some things are going to have to change. OK? This is just like our count ordered list. We're going to keep the list in order as we add the keys and elements. So just like you did on that first calendar assignment, right, you need to actually figure that out. Well, I think we're going to need a little more space for this. Our insert item. Oh, man. Remember all this stuff we had to do? Like, this was like nightmare stuff, right? Insert item. Oh, man, there's special cases. You have to keep, things. So first we expand if we need to. Then we have this special case for the first element, right? You can put it in. You have to remember to return. Lots of people didn't return, right? Don't forget to increment your size. Then you keep it ordered, right? And if we're keeping it ordered, we have to find the spot to go, where it's going to go. And then we have to do some bunch of moving, one direction, right? If we find it's in the middle, you move everything up one and then plop it right there, right? Remember all that? We did all that for our first calendar assignment. There's all this stuff, and then you've got all these different situations, right? And then if it's at the end, you might not have figured it out here. You got to put it at the end, right? Special cases, blah, blah, blah. Well, but remember, we're getting the benefit of all this. The benefit will be when we want to find the min, we got it, right? We know where it is. OK? What's the asymptotic behavior of this? Is it on squared? I think it's just on, actually. Let's think about it. Do you have two? You have this for loop goes up to the size, but we're returning if we find it, right? And if we don't find it, or if we do find it, then we have to go the rest of the list and move everybody over. So inserting is not on squared, although you have to be careful. That's actually a very good point. You have to be careful. Seeing two for loops does not necessarily mean it's on squared if you're breaking the loop into two parts, which we're doing here. Finding the element, moving everybody else up, plopping the element in. OK? Make sense? I see some people going, no, I don't get it. It makes sense that let's look at the actual. We go from here. We start out and we say I equals 0. I is less than the whole. So it looks like we're going through the whole thing. If we find it, which means we got here, and we found where the key is less than the key in the place that we are is less than the key that we want to stick in there, right? Then you actually have to, you go for the rest of it. You start at the side, and then you go down, actually. It's kind of ugly, and you have to move everybody back up. But when you add those two numbers up, it's only the total numbers of elements in the actual array. OK? OK. All right, so anyway, order n gets a boo from us. So we're going to keep it, but remember, we've got this great benefit from it, right? Order n, it's going to get boo, but that's all right. This is the insert item for an ordered list. OK. So let me move here, and I'll just write this down. OK, so that's that one. Then we're going to have ordered list. Actually, I'll do it this. I didn't do this very well. Here, this will be unordered, like this. And this one will be ordered. OK, and this one is now going to be order n, like that. Like that. There we go. OK. All right. So then now, look, we're going to now do the min element. Whew. All of that work we did to sort our priority queue ends up, our min index loves us right now. Take a look at this. Our min index returns the size -1 because our minimum we kept at the end every time. Right? We sorted it such that the minimum was always at the end. We don't need to move anything. It's always the one at the end. All we need to do is return the size -1 when we want to find our min index. Woohoo, right? We're like really happy with that. And this is exactly the same. Nothing has changed here. We're just finding that min index and doing it. That is great. One operation means that what's the asymptotic behavior? Oh, 1. Min element, oh, 1. Awesome. Okay, that should get a yay. Yay. Okay. All right. Remove element. Right? Remove min, I should say. Remove min. All right. First things first, we check and see if it's empty. If it is, we've got our error. Okay. If it is empty, we find the minimum. Okay. And then we have to do what? Do I need to do all this? Oh, yeah, we do. I left this the same for a reason. OK. We have to do this. We find the minimum. What's the minimum going to be? What did we say it's already going to be? It's going to be the last element because it's sorted. Let's see our little loop here that kind of foiled us before. We're going from the min index down to the size of the priority queue minus 1. If it's the last one, how many do we have to go through this loop? How many times do we have to go through this loop? None, right? Take that right out. You don't even need it there. I mean, I put it there because just to show you that this doesn't even need to change, but you get the benefit of it being perfectly sorted already. Yes, that's great. We do have to remember to decrement the size. Asymptotic behavior for this one? Oh, 1. All right. So there's your trade-offs for using these two methods. You get O1 for inserting into this guy, but then both min element and remove min ON. You get ON behavior for order n behavior for inserting, because you got to keep it sorted every time. And then you get the order 1 when you're actually doing the removals. Not bad. OK, the removals and the finding the minimum element. OK. So let me see. Is this the O1 yay? Right, we get that. OK. Let me show you. I built this, and you can test it if you want. And oops, I'll do it over here. OK, let's see. I think it's right here. OK, so here's what I built. OK, it's not there. Hold on. It is here. And there it is. OK, so I have a couple things here. I've got an unordered situation, and I've got these word priorities in here. OK, the word priorities was the following. I took the dictionary that they gave us. Now, the dictionary on my Mac, instead of being 470,000 or 30,000 words, is like 230,000 words. But it's still a lot of words, right? In fact, let me show you what it looks like here. Let's see. ls word priorities.txt. Oops, sorry. Less word priorities.txt. OK, so here's the word list. I randomized it. OK, and I prioritized it. What I did was I took the list in alphabetical order, and I said the first word gets priority 0, the second word gets priority 1, so on, all the way down to the z's, which don't get very high. They get really low priority, right? And I took a look at this, and then I sorted it, or sorry, then I shuffled it, right? And then this is what came out. So you've got hearsay, which happens to be 83,084. Whatever that is. Photo vitro type is 145,522 out of this list. Right? And the list is word count word priorities.txt is 235,000 words long. OK, fair amount of words. What we're going to do is I'm going to put this into my unordered priority queue. OK, unordered. We said that the insert is O1. Should my inserting into this queue for all 235,000 words take a long time? It should not. Okay. Then I'm going to find a number of the elements, min elements. Then I'm going to remove a bunch. Actually, I think I just removed them, as it turns out. Right? And I'm going to remove 100, then 1,000, then, or maybe it's 1, then 10, then 100, then 1,000, something like that. And what it's going to do, by the way, is it's going to print out all of the, it's going to print out as it's inserting them when it gets to 1,000, then 2,000, then 3,000, then 4,000. You'll see what it does. But it's going to scroll down a bunch of numbers. Those numbers represent how many items have I inserted so far. OK? Boom. All right. It's flying through. Did you see how fast it did that? Put 235,000 in there like that. OK. The size was 235,886. Took 1.3 seconds to insert those. To remove one of them took very little time, 0.004 seconds. To remove 100 of them took 0.28 seconds. To remove 1,000 of them, isn't this asymptotically order n behavior? So about 10 times as long to remove 10 times as many, right? Now I'm removing 10,000. How long are we going to have to wait? Yeah, about 28, 29 seconds, something like that, right? Oh, a little bit longer. Could have been for a lot of different reasons. But in fact, it could have been for a lot of different reasons, depending on which ones I happen to decide to remove, right? Or which ones happen to be minimum in the list and where they happen to be in the list, right? OK, so we saw that behavior. OK, 33 seconds to do 10,000. All right, but the inserting, almost no time. OK. What if we did it with an ordered list? Let's check. OK, we'll do the exact same thing, except now we will do an ordered list. OK, and oh boy, what's going on here? It's sped through the first 10,000 or so pretty quickly. Now what's happening? Oh man, can you tell that it's even getting? You can see it slowing down, right? It's like 61. Oh, it's so much harder. Why is it doing that? Right? Why does it have to do that? Slow down like that. Why is it getting slower and slower? It has to go through the list, and the list keeps getting bigger, right? If I let this go, this is just this. I think on my computer it took, on my other computer in the office it took something like 3 or 4 minutes to do this. I'm not going to make us sit through this whole thing, right? 3 or 4 minutes. I'm going to cheat a little bit. What I'm going to do is I'm going to stop this because that's going to take a while. It's still, and by the way, it's still getting slower and slower and slower, right? Right? Asymptotic is slower and slower. So it's going to just, by the time it gets to like 230,000, you're like, oh, hurry up, right? Well, OK, so I'm going to cheat a little bit. Instead, I actually put I put a list together in order, right? So I kind of cheated, right? I've got a word priority list in order, right? And actually, what I want to do is this. Less word priorities in order. And it's backwards, right? Because if I'm always putting an element I'm always putting it after the last element, right? I don't actually have to move any of the elements. Because if I'm inserting in the thing and I have to, and something's less, I will have to move everything backwards, right? I'm not going to do that. So I'm going to put them in like this. And it's going to cheat a little bit. But let's see what happens. Priority queue ordered word priorities in order.txt. OK, so it's going much faster now. It is still going to slow down. In fact, it still takes a little bit of time. So I kind of have to make up the time by talking, right? I should learn some jokes, right? Remind me, I'll tell you my Army jokes and my Air Force jokes someday. But so anyway, it's gonna do this. Now we'll wait for it, right? It is slowing down, and but it's not terrible. And the reason it's not terrible, again, we don't have to do all that moving around. OK, I'm cheating, but in the interest of trying to continue, I guess I could have just let the other one go. It might have been finished by now, maybe, might have been. But so this is where you're losing time here, right? Like right now is where you're losing time. If you're gonna put this in here, we have to get all the way up to 235,000, and it's got to go through that list every time, and it's at least got to get to the end. And then do the thing. There's no moving though, so it's going to take a little bit better, but 235,000. How fast is the actual remove min going to be? Order 1, right? So it's still cranking away here. It's finally going to get, there we go, boom. All right, look at that. OK, I mean, it took like it can't even figure out how much time it took to remove 1. Right? It's so fast, it won't even, the timer I used, which it didn't go down all the way to that many things, but it like went down to like, let's see, that's 5 microseconds, right? 5 microseconds, or 6 microseconds, right? Which is not very much time. All right, and then to do 1,000 of them, or 10,000 of them only took 61 microseconds, right? Because it is constant time removal, right? We like that. OK, we like that. But look how long it took to insert them all. 70 seconds. Do you remember how long it took to do the entire 10,000 before with the other one? I don't even remember. It was like 28. It was 28 seconds plus another like 2 seconds or 3 seconds plus another like how many seconds to insert? 1.3. So it actually worked out better for this use case to do the unordered one for only 10,000 deletes. It removes. Yes.
If we were going to remove everything, would the unordered take like the same amount of time? Because we only remove.
If we were going to remove everything from the unordered, it would be really slow. Yeah, it would be really slow. Why? Because asymptotically, you're talking about that. Yeah. If you were to remove everything from the ordered one, easy. You just walk down the list and do it. Yeah. Same.
Would the unordered get faster and faster as you remove it?
It would. The unordered would get faster and faster. I mean, anytime. In fact, I kind of cheated here. I didn't like restart the whole list here. So yeah. So removed one. Now there's only one less, one fewer. Now there's 100 fewer, 1,000 fewer, 10,000 fewer. So these numbers you can't quite rely on in the sense of like absolute, doing that. But yeah, it would get faster. Yes.
So even though like my initial guys thought was that since the unordered had 2 O's to the end, it would always be slower. But so it depends on how many you're inserting and how many you're removing.
Exactly. It depends on how many you're inserting. It depends on your use case, right? If you can put together an ordered dictionary like the one that, so the ordered dictionary that I showed you earlier is already ordered, right? Somebody at the Linux consortium pushed a button to order that list, and now it's in order. And if you never have to make another, you never have to order it again. How many times do you add words? Once every couple of years, maybe, right? So you never have to order again. Then you would definitely get the benefits here because you only have to do that once. Now, if you're putting a bunch of things in this ordered list and then removing a bunch of or removing only a couple, well then this would actually work out. So it's totally based on your usage case. Yeah. Okay. Yeah. Ian?
What makes what leaves in order faster but still slow?
Say again.
And it's still order n, but it's faster.
It's a faster order n. We are generally not going to worry about the differentiation between faster order n versus another slower order n in general. Sometimes we may worry about that. But remember, best case, worst case, we're worried about the worst case in general. Yeah. Okay?
That depends on the coefficient of n.
Yeah, it depends on whether or not that happens to be 5 times or whatever. But we are not going to stress out about that. Yeah. Okay? And in this case, like deleting and moving all those elements does take more time because of the, it would matter in that sense, but we're not going to stress about that. We're not going to worry about that. Okay. Any other questions? All right, over the break, well, you're not going to quite get there, but we've got like 3 weeks before our next new class. We're going to come back to priority queues. Okay, and we're going to come back to priority queues and say, this really isn't that great overall. We've got trade-offs here, but they're not good trade-offs. And they work for your use cases, but in general, they don't work so well. So there might be a better way to think about that. All right, see you guys Monday or in lab.